This is Chapter 2, Analyzing Data, Section Point 3, Uncertainty in Data. The objectives of this lesson are to define and compare accuracy and precision, describe the accuracy of experimental data using error and percent error, apply rules for significant figures to express uncertainty in measured and calculated values. Some vocabulary to review is experiment, and some new vocabulary is accuracy, precision, error, percent error, and significant figure. Just as you measure a teaspoon in the kitchen, might not always be exactly a teaspoon. You might go a little over, you might go a little under. Same thing happens in the laboratory. When scientists make measurements, they evaluate both the accuracy and the precision of the measurement. Although you might think that the terms accuracy and precision basically mean the same thing, to a scientist they have totally different meanings. Accuracy refers to how close a measured value is to an accepted value, whereas precision refers to how close a series of measurements are to another. Let's use this example below of an archery target. All right, an archer is aiming for the bullseye. And if he's aiming for the bullseye and hits the bullseye, he's pretty accurate, right? However, if he were to go ahead and shoot 3 arrows, and he landed within the same area, but not the bullseye, we can say that his shot is pretty precise in a given area. However, it's not accurate to the bullseye itself. If we were to go ahead and look at that archer, and he would go ahead and improve their shot, and he made 3 shots within the bullseye, we can go ahead and say that, well, that archer's not just accurate, but he's also precise as well. Now again, if you're new to archery and you just start shooting at the target, chances are you're going to have a target looking like this, right, in which you have arrows that are not clustered within each other, and they're nowhere near the bullseye itself. So we would go ahead and say that this case, right, the archer is not accurate and he is not precise. And if we go ahead and look at the data above in this table, students were asked to find the density of an unknown white powder. Each student measured the volume and the mass of the 3 samples and then reported their densities for each trial and then average of these 3 calculations. This white powder turned out to be sucrose, or just table sugar, and table sugar has a density of 1.59 grams per centimeter cubed. When we look at this, we could ask ourselves which student collected the most accurate data. Right? In this case, which one came closer to the bullseye? Who collected the most precise data? And if we go ahead and look at this, student A's measurements are the most accurate because they are closest to the accepted value of 1.59. In this case, he took the densities and averaged them, and he got the data here, which was to be the most accurate. Student C's measurements are the most precise because they are closer to one another, even though they're not closer to the accepted value of sucrose. They tend to be within, what is that, about 200ths of a gram per centimeter cubed. Whereas if we go ahead and look at student A, it looks like that they were in about 600ths of a gram per centimeter cubed. Recall that precise measurements might not be accurate. Looking at just the average of the densities can be misleading. Based solely on the average, student B appears to have collected fairly reliable data. However, on close inspection, student B's data are neither accurate nor precise. Again, if we take a look at student B, right, we can see that he's kind of all over the place here. But again, when we go ahead and take the average, right, it seems like he did pretty well. But again, if we look at the raw data itself, we can go ahead and see that student B was not accurate, nor was he precise in making his measurements. The density values reported in that table are experimental values, which means that they are values measured during an experiment. The known density of sucrose is an accepted value, which is a value that is considered to be true. To evaluate the accuracy of experimental data, you can compare how close the experimental value is to the accepted value. We use error to define, error is defined as the difference between an experimental value and an accepted value. The errors for the experimental densities are also given in the table 2.3, and that's what we see over here. What is the difference between your average, your accepted value against your experimental value? And again, it's just nothing more than a difference. You're just taking the difference between your experimental value and your accepted value, and that's what we call error. Scientists often want to know what percent of the accepted value of an error represents, and that's where percent error comes in. Percent error expresses error as a percentage of the accepted value. So what we do for percent error is you take that above equation, right? Experimental value minus accepted value, and take the absolute value of that. We don't care if it's negative or positive. We just want to go ahead and know the magnitude of that error. So we just go ahead and take the absolute value of that, and then we divide that by the accepted value, in this case the density of sucrose. So we take that error, divide it by the accepted value, and multiply it by 100. And the percent error of an experimental value equals to the absolute value divided by the accepted value multiplied by 100. Again, why is it that we use the absolute value? Is because we don't really care about the size. We don't care about the magnitude, whether it's positive or negative. We really only care about the size in which the error was. So we just go ahead and take the absolute value of that. Percent error is an important concept for machinists who use this nut on the side. Right? The machinists use to go ahead and check the tolerances of the nut. The tolerances are a narrow range of allowable dimensions based on acceptable amounts of error. If the dimension of the nut does not fall within the acceptable range, they would have to go ahead and discard of anything that is out of spec. All right, so calculating percent error. Let's use student A's density in the table above to calculate the percent error in each trial. And we're going to go ahead and report that to 2 decimal places after the decimal point. All right, so you are given the errors for a set of density calculations that was all provided to you, right? So what we go ahead and do is we look at those errors, right? We know that the accepted value is 1.59 grams per centimeter cubed, and we know that the error is negative 0.05 grams per centimeter cubed, a positive 0.01, and a negative 0.02. So we want to go ahead and find out, well, what is the percent error of these values with respect to the given accepted value for the density. So all we have to do is just take our errors, our experimental errors, right? We're going to go ahead and take the absolute value of them and then divide by the accepted values here. So again, negative 0.05 just turns into positive 0.05, and then we divide it by the accepted value, in which this case is 1.59, and we multiply it by 100. Right, in this case, his first run had about a 3.14% error. His second run was much better with a 0.63% run error. And then on his third try, they got a 1.26% error. Significant figures. Often precision is limited by the tools available. For example, a digital clock that displays the time as 12:47 or 12:48 can report the time only to the nearest minute. However, if we're going to go look at a stopwatch, you might record time to the nearest hundredth of a second. As scientists have developed better measuring devices, they have been able to make more precise measurements. Of course, for measurements to be both accurate and precise, the measuring device must be in good working order. Additionally, accurate and precise measurements rely on the skill of the person using the instrument. The user must be trained and use proper technique. The precision of a measurement is indicated by the number of digits reported. A value of 3.52 grams is more precise than a value of 3.5 grams. The reported digits are called significant figures. Significant figures include all known digits plus one estimated digit. If we were to go ahead and consider the rod down below, the end of the rod falls between 5.2 and 5.3 centimeters. Here's that image right here, right? We have this rod, and if we were to go ahead and put a ruler to it, we see that we know it is 5 centimeters at least. We can also go ahead and look deeper into that, and we can see that it also has about, it's inched over the 0.2 centimeter line, but it falls somewhere between 0.2 and 0.3 markings. So because of that, we don't want to go ahead and cast away any sort of significance that it falls in between there. So what we can do is we can just go ahead and look at that, and then we can go ahead and make an estimate of what that value might be when it falls between the 2/10 and the 3/10 marking. So we go ahead and just call that 0.03. Right, and again, that could be arbitrary up to the observer. There's nothing to say that it couldn't be 0.02 or it couldn't be 0.04. Right? However, it falls in between those two markings. Remember that measurements reported with a lot of significant figures might be precise but not accurate. For example, some chemistry labs have balances that report masses to the nearest hundredth of a gram. You and each of your classmates measured the same copper cylinder on the scale. You would probably have a group of very precise measurements. But what if the scale had been properly damaged? But what if the scale had been previously damaged by an object that was too large for it? Your precise measurements would then not be accurate. So let's just kind of go through recognizing some significant figures and taking some problem-solving strategies when doing this, right? Learning these 5 rules for recognizing significant figures will help you when solving problems. Examples of each rule are shown below, and note that each of the highlighted examples has 3 significant figures. Rule number 1 is that non-zero numbers are always significant. Right? In this case, none of these numbers are 0, so therefore they are significant. Zeros between non-zero numbers are always significant. In this case, we have 60.5, right? So that 0 in this case is significant. Rule number 3, all final zeros to the right of the decimal are significant. In this case of 6.20, because that 0 is stated, right, it is considered significant. However, in rule number 4, placeholder zeros are not significant. To remove placeholder zeros, try writing it in scientific notation. In this case, right, we have 0.0253. These 2 zeros are not significant. Just as if we had 4,320, this 0 right here is not significant. And what we say is that each of these have 3 significant figures, right? Now, which is highlighted in yellow. And rule number 5, counting numbers and defined constants have an infinite number of significant figures. So in this case, 6 molecules, right, has infinite number of significant figures, and 60 seconds is equal to 1 minute. And why we go ahead and say rule number 5 is because when we do dimensional analysis and then the question comes up quite frequently, we just go ahead and take these numbers to have infinite number of significant figures so that we don't use these rules to go ahead and determine what the value, or I should say, how we report the answer in terms of significant figures. So it's almost as if we just ignore these in the rules of addition and subtraction, multiplication, division of significant figures. All right, determine the number of significant figures in the following masses. We have two numbers here, right? Let's look at them. You are given two measured mass values. Apply the appropriate rules to determine the number of significant figures in each value. If we were to go ahead and look at this, remember that the rule says any placeholder zeros are non-significant. Right? In this case, we have these placeholder zeros. Right? But also notice how after the decimal, this 0 had been noted. Because this 0 is noted, we call that a significant 0. In this case, if we were to go ahead and count them, we have 1, 2, 3, 4, 5 significant figures. If we were to go ahead and look at the next one, right, we have these placeholder zeros, but we have these numbers which are considered significant. So we would go ahead and write this, note this as 3 significant figures. If we wanted to go ahead and write them in scientific notation, and it would look a lot like this. Rounding numbers. Calculators perform flawless arithmetic, but they are not aware of the number of significant figures that should be reported in answers. For example, a density calculation should not have more significant figures than the original data, with the fewest significant figures. To report a value correctly, you often need to round. Consider an object with a mass of 22.44 grams and a volume of 14.2 centimeters cubed. When you put the calculation, right, mass over volume, into your calculator, right, you're going to get a value that looks something like this, right, in terms of grams per centimeter cubed. Because the measured value had 4 significant figures and the measured volume had 3 significant figures, it's not correct to report the calculated density value with 8 significant figures. Instead, the density must be rounded to 3 significant figures, or 1.58 grams per centimeter cubed. Consider the value, yep, you know it. I'm just going to highlight it. Right? How would you round this number to 5 significant figures, to 3 significant figures? In each case, you need to look at the digits that follow the desired last significant figure. To round to 5 significant figures, first identify the 5th significant figure. In this case, it is 0. And then look to the right of that number. Right? In this case, it's a 1. And here, we do not change the last significant figure if the digit is less than 5. Because 1 is less than 5, we go ahead and just leave the number rounded to the 0. If the number had been greater than 5, we would go ahead and round that up. Right? That 0 would then become a 1. So now let's go ahead and look at this if we were to go ahead and estimate this based upon 3 significant digits. Right? In this case, our 1 is our significant digit, and we're going to go ahead and look at 5. Because 5, right, falls in that 5 or greater rule, what we do is we go ahead and round that 1 up. So then we report an answer of 3.52. Here's a little problem-solving strategy for rounding numbers. Learn these 4 rules for rounding and use them when solving problems. Examples of each rule are shown below. Note that each example has 3 significant figures. If the digit to the right of the last significant figure is less than 5, you do not change the significant figure. Right? So in this case, we're looking for 3 sig figs. 3 is the number that we're going to be focusing on. And then look at the digit following. Because 2 is less than 5, we leave it as is. If we had this number, right, again, we want to have 3 significant figures in our answer. If it is greater than 5, right, this 6 is greater than 5, we are going to go ahead and round up, which is 2.54. If the digit to the right of the last significant figure are followed by non-zero digits, right, round up to the last significant digit. Right, so in this case here, right, we have more than what we're looking for. So we're going to go ahead and take that 3, look at the 5, and say, okay, because it follows the rule as that of number 2, we go ahead and round it up. If the digit to the right of the last significant figures are a 5 followed by a 0, or no other number at all, look at the last significant figure. If odd, round it up. If it's even, do not round up. So in this case, here we have 2.5350. Because it's an odd number, 3 is an odd number, and we look at the 5, we're going to go ahead and round it up to 2.54. But because we're dealing with here a even number, 2 is an even number, we're going to go ahead and leave it as is, and we're just going to go ahead and leave it as 2.52. Addition and subtraction. When you add or subtract measurements, the answer must have the same number of digits. I'm going to highlight this. This is important. When you add or subtract measurements, the answer must have the same number of digits to the right of the decimal as the original value having the fewest number of digits to the right of the decimal. For example, 1.24, 12.4, and 124 have 2, 1, and 0 digits to the right of the decimal respectively. So when adding or subtracting, arrange the values so that the decimal points align. Identify the value with the fewest places after the decimal point, and then round your answer to that decimal point. Multiplication and division. When you multiply or divide numbers, your answer must have the same number of significant figures as the measurement with the fewest significant figures. I'll go ahead and explain some examples for you. A student measures the length of his lab partner's shoe. If the lengths are 28.0, 23.538, and 25.68 centimeters, what is the total length of the shoe? The 3 measurements need to be aligned so that the decimal points and added. The measurement with the fewest digits after the decimal, point to 28.0, while with 1 digit. Thus, your answer must be rounded to only 1 digit after the decimal point. So when we go ahead and add these numbers up, we get 77.218, and because we only have this number right here with 1 significant figure after the decimal, we must report our answer to only 1 significant figure. And again, if we were to look at this 2, right, we go ahead and look at the 1, and because 1 is less than 5, we're just going to go ahead and leave it as is. Now what about multiplying and dividing? All right, calculate the volume of a book with these following dimensions: 28.3, 22.2, and 3.65. Right? just recall that volume is length times width times height. So if we were to go ahead and take all of these values, right, when we take all of these values, we see that we get this answer right here when we get the product of the volume. That's a lot to go ahead and report because a lot of these numbers are just insignificant. So what the rule states is that we want to go ahead and find which of these has the least amount of significant figures in total, not after the decimal, just in total. So here we have 3 sig figs, 3 sig figs, and 3 sig figs, right? So our answer should be reported with 3 sig figs. So we take the numbers that are most important, the largest of them, which is these right here. Now at that 9, we're going to go ahead and look at the 3 and ask ourselves, are we going to go ahead and round up that 9, or we're going to go ahead and leave it? Because 3 is less than 5, looks like we're just going to go ahead and leave it. And all of these numbers are just kind of clumped into this 0 right here. So the volume of our book would just be 2,290 centimeters cubed. Section summary. An accurate measurement is close to the accepted value. A set of precise measurements shows little variation. The measurement device determines the degree of precision possible. Error is the difference between the measured value and the accepted value. Percent error gives the percent deviation from the accepted value. And the number of significant figures reflects the precision of reported data. Calculations are often rounded to the correct number of significant figures.